welcome to my channel. So in the last video we have introduced a minimum spanning tree. So and also we have seen the concept of spanning tree, how to get into a minimum spanning tree, all these things. And to achieve the minimum spanning tree or to create a minimum spanning tree, we have two algorithms. One is Prim's algorithm, the other one is Kruskal's algorithms. Okay. So regarding the minimum spanning tree, the goal is to create a graph with no cycles, or else I can say that simply I have to create a acyclic graph with a minimum edge cast. This is the main goal of minimum spanning tree. So to create that, we have several algorithmic procedures. So first one is Prim's algorithm. So Prim's algorithm is like, the steps is like you have to start with any vertex. Okay, you can just start with any arbitrary vertex and you have to continue to add all the edges with the smallest weight. So in this Prim's algorithm, we have to concentrate on the adjacent vertex from the chosen vertex. Okay, but in Kruskal algorithm, we won't consider the adjacent vertex. So you will be seeing the depth understanding of Kruskal algorithm in the next video. But in this video, we have to concentrate on the adjacent vertex. So the steps are, first we have to initialize and minimum spanning tree with a randomly chosen vertex. Any vertex you can choose, that is a source of the your path or a graph, your minimum spanning tree graph. Okay, so now we have to find all the edges that connect the tree in the above step with the new vertex. From the edges we have to select the minimum edges. So we can have like n number of possible edges from that particular vertex. So from that, like n number of possible or linked edges, we have to choose the minimum edge, and then that you have to add it to the minimum spanning tree. Okay, so this has to be repeat until your goal is reached. What is your goal? You have to create a graph without any cycle or a loop. That is our goal. Okay, so regarding the applications of Prim's algorithm, this can be used in network designing, your the net of electric wiring cables, all these things. So applications I have been like depthly covered in minimum spanning tree video. Please see that video and come back to this Prim's algorithm. Okay, so now let's see an example. Okay, so here is given a weighted graph, undirected weighted graph. So this is your given original graph. So from this original graph, we have to draw a minimum spanning tree or create a minimum spanning tree by using a Prim's algorithm concept. Okay, first step is we have to choose any random vertex from the given graph. Okay, so in this example they have chosen randomly a B as a source vertex. Okay, so here B is the chosen vertex from the above graph. This is your first step. Second step, you have to get into the adjacent vertex of B, because this is a vertex we have chosen, okay, as an initial vertex. From this vertex you have to see like what are the adjacent vertex. So we have two edges here. From B I can travel to D, and from B I can travel to C. So we have BD and BC. From the two adjacent vertex you have to see that which is very minimum. Okay, you have to take that and you have to add with that. Okay, so you can just see here. So we have B2C is 10 and B2D is 4. So among the edges we have BD which has a minimum weight. So let's add that to the minimum spanning tree. So now BD has been added. Okay, this edge has been added because it has a minimum weight. Now let's look into the other edges. Okay, one by one. Okay, now we'll just see the adjacent vertex of D. Okay, just go to the original graph and see what is the adjacent vertex of D. So we have C and we have E. So B is also there, which already we have just completed. So from D we have to travel to C with a cost of 2, and from D we have to travel to E with a cost of 1. So from the two edges, which is minimum, DE is a minimum. So that we have to add it into the minimum spanning tree. So now we have added. Okay, so now we have added DE because DE has the minimum weight when compared with the other edge. Now you just go with E. Okay, so what are the adjacent vertex of E? Okay, just go to the original graph and see. From E I can have to travel to C and D. So D is already given, only I can take up C. because no other go, there is no combinations or there is no comparisons of edges. So we just simply draw E and C with a weight of 6. Okay. So when you're just adding up with that, so what happens? So when you're just adding up with that particular thing, we'll be having EC. So here, okay, so EC is 6. Okay, but we have added, yeah, we have added this also. Okay, when you have for C, we have 6 and 2. Okay, so which is minimum again. Okay, from here we have from E and to C, again we have D to C is also there. So for C we have two edges, actually the adjacent vertex of that. So we have 6 and 2, which means that 2 is minimum, so that has been added here. Okay, so that's the thing. Fine. Okay, so we have added a DC here with a weight of 2. Okay, so again for the C, what are the adjacent vertex? For the C we have A with a minimum cost of 3. Okay, we have added that. Okay, the edges of AC has been added with a weight of 3. So now all the vectors has been connected. Okay, so now you can see all the vertex has been visited. So A is visited, C is visited, E is visited, D is visited, and B is visited. So all things has been added up. So now what you have to do, you have to sum up all the weights. So you just take up 4 plus 2 6, 6 plus 1 7, 7 plus 3 10. So total of this minimum cost edge cost is nothing but 10 units. Okay, so this is, you can see the graph, the minimum spanning tree graph. So there is no cycle. Okay, so this is satisfies the first property of minimum spanning tree. Second thing is like we have the minimum edge cost, which is 10 units, because we have chosen all adjacent vertex with a minimum edge only, that only we have added. Okay, so in this regard we'll be getting only the minimum cost or minimum edge cost. So if you are solving the same graph by using Kruskal algorithm, you get the same value. Okay, same minimum spanning tree cost. You can just try in your home. Take up this graph, first understand the Prim's algorithm, solve it by using Prim's algorithm, then go to the next video, understand the Kruskal algorithm, and then try to solve this graph in Kruskal algorithm. You see that same total cost, total edge cost will be there, okay, for Kruskal algorithm also. So when you're just creating a minimum spanning tree from the original graph, either by using Prim's or Kruskal, same value will be, or same total cost will be thrown for both the algorithms. That is the high magic of minimum spanning tree algorithms. Okay, you can use any algorithm. The thing is, like in the question, if they mentioned any like specific Prim's or Kruskal, you have to follow that procedure to create a minimum spanning tree. If they blindly given a given graph and you just asking to create a minimum spanning tree, you can choose either which algorithm is comfortable for you. You can choose any algorithms. Okay, but both algorithm will give us the same total edge cost. Okay, nothing different. Okay, so this is how your Prim's algorithm has to be solved. Just I'll repeat it how to solve it again. So from the original graph, get the choose the arbitrary vertex, any random arbitrary vertex. From that vertex, you just go to the adjacent vertex and see that which is like very minimum. Then add that edges to the minimum spanning tree. Okay, again from that you have to just take up the adjacent vertex and see that is there any other thing is like which is minimum, all these things. So from D we have C and E, and here again we have just taken the minimum thing, but here like E to C is 6 and again we for C we can just have from D also, that is very minimum. So that's why we have taken D to C. Okay, so this is how you have to solve it by using Prim's algorithm to create a minimum spanning tree from the given graph. Okay, and finally don't forget to give the total edge cost of the minimum spanning tree. You have to give that numerical value by summing up all the weights of the output minimum spanning tree. Okay, so if you have doubts, please ping me in comments. Thank you. Happy learning.